Hello, hello, and welcome back. Here is our lecture for today. Last time we got into the integrated rate laws. We did first and second order rate laws. Now we're going to get into something that most of you have probably heard of, but maybe not in so much detail, and that is something called a half-life. Okay. A half-life which is symbolized by this little T1/2. That's the half-life of a substance. Is simply the time required, the total time required for half of a reactant to react. Okay? So if you start out with 1 mole of reactant, the half-life would be the time it takes for the reactant to reach a concentration of 0.5 moles. Okay? So for example, if I have a T1/2 for some substance of 100 seconds, that means that if I have an A0 equal to 0, or well, let's just use the same as we did before, 1.0 molar. Okay. Therefore, at 100 seconds of the reaction, okay, so at 100 seconds of going through the reaction, the concentration of whatever species at that time, T equal 100, is going to equal 1/2 of this guy here. Okay, so that would be 0.5. Okay, so that's all the half-life really means. And it's as you'll see in just a little bit, it's a very interesting and useful thing to talk about. Okay? So let's go through all of the different types. We'll start with first order. Okay? So first order, we can derive the half-life for a first order reaction by starting with the integrated rate law. Okay, so I'm going to write it a little bit differently than you guys have seen it. You guys can go back to the integrated rate law for the first order and verify that the way that I'm writing it is equivalent to the way that I wrote it earlier. Okay? So we can rewrite this as ln of AT over ln of A naught is equal to negative KT. Okay, now at T equal half-life. Okay, at T equal T1/2, A sub T1/2 is equal to 1/2 A naught. Yeah, that's what being at the half-life actually means. So we can actually sub this in up here. Okay. So now we have natural log of 1/2 A sub naught divided by A sub naught is equal to negative K times T to the 1/2. Okay, so that's now the half-life. Nice thing that happens here is that these guys just both cancel out. So we're left with a natural log of 1/2 on this side is equal to negative K T 1/2. Okay. Now to get to the half-life, all we have to do is divide the natural log by negative K. So if I just divide both sides by negative K here, then I get T1/2 in this case is equal to the natural log of 1/2 over negative K. Okay. Now, natural log of 1/2, this is a constant value, and so we can, no matter what the rate constant is, we can always write this as T1/2 is equal to negative 0.693. That's the value that you get from ln of 1/2 divided by K. Oh, bad K, sorry. Divided by K. Okay, so this is Oh, wait. Oh, I'm sorry. This is divided by negative k. Okay? So you get the negative 0.693 from ln of 1/2. Let me just write that explicitly because that was a little confusing. Is equal to negative 0.693. Okay? So then I plug that back in here. I have a negative over a negative. And so we end up with t1/2 is equal to 0.693 divided by k. Okay? This is the half-life for a first order reaction. Okay? This is the point, oops, I need to switch back to black. This is the point at which the initial concentration is cut completely in half, exactly in half, at this exact time. Okay, so anytime you have a first order reaction, you can always use this formula to find the half-life. And as you can see, this whole equation is independent of the initial concentration, okay? Which is interesting. So it's always going to be the same, depending, or it doesn't matter what your initial concentration is. The time it takes to get rid of half of it will always be the same, and it's only dependent on the rate constant for that reaction. Okay, so if we look at a graph of this over time, let's see how concentration. So this is concentration on this axis. See, concentration on this axis, and this is time down here on this axis. Okay, so let's look and see how this evolves over time. If we start out at 1.00 molar, this is half, so this is the first half-life, so 0.5 molar. Okay, and as we go down, a first order reaction looks kind of like this. Let's see if I can draw this okay. Okay, something like that. So at exactly half concentration is here, so around here, and then this is the first half-life. Okay, so this distance here is t1/2. Okay, now we can cut this concentration in half. So instead of going from 1 to 0.5, we can go from 0.5 to 0.25. Okay, and as we cut this in half, there should be another exactly the same value of time between these 2 points. So right there. So this should be the second half-life. So this should be equal to t1/2. Remember, because it's not dependent on the initial concentration, so we can treat the initial concentration as 0.5 or 1.0, and we should get the exact same value. Okay, so t1/2 here is equal to t1/2 here, because it does not depend on the initial concentration. And we can do the same thing again with 0.25. We can cut that in half and get 0.125. Okay, and that goes all the way over to here, and we get another t1/2 over here, and again, it should equal the other two. Okay. And one thing I want to point out here, as you see, this is the point at which 2 times t1/2 has been reached, right? But you can see that there's still 0.25 of the concentration left, okay? So 2 times the t1/2 does not equal reaction time. Okay, and this is simply because after you go to half the concentration, you can start over again and go half the concentration again, and go half the concentration again, etc., etc., etc. Okay, so 2 times the half-life does not equal the total reaction time. Sometimes that confuses people. The half-life does not really mean half the reaction time. It just means half, or the amount of time it takes for half of the reaction to react. Okay, let's do second order now. That was first order. Let's do second order. if we start out for the rate law for second order processes, the integrated rate law, that looks something like this, 1 over a naught. Okay, so we have concentration versus time, and we're going to do the same trick. So at t equal t 1/2, sorry, yeah, that's right, a t is equal to 1/2 a naught. Okay. So let's plug this guy back up in here and see what happens with this equation. So we end up with 1 over 1/2 a naught is equal to k t 1/2 plus 1 over a naught. Okay. That plus sign. Now all we have to do is solve for t 1/2. So let's begin by bringing this over to the other side by subtracting from both sides of the equation. So we end up with 2 over a naught from this guy minus 1 over a naught is equal to k times t 1/2. Okay, so 2 over 1 or a naught minus 1 over a naught is equal to 1 over a naught. So then that means that 1 over a naught is equal to k times t half. Okay, now we just divide both sides by k, and we get t 1/2 on a side by its own. T 1/2 is equal to 1 over k times a naught. Okay, so for a second order process, the half-life is equal to this. And the interesting thing about this versus the first order process is that now this is dependent. It depends on the initial concentration. Okay, so it's no longer independent of the concentration. Now it depends on the concentration, which means that as a naught gets smaller, the half-life gets larger. Okay, so this means that as the reaction progresses, a naught's going to get smaller and smaller. This means that the half-life gets longer and longer and longer as the concentration decreases. Okay? So if we look at this on a graph, so this is concentration here, and let's start out at 1.0 moles. The way that this looks is kind of like that. Okay, so then we have this kind of, oh man, I'm gonna take that back a second. Okay, I'm just gonna color that over. That's about halfway. We'll call it halfway. Okay, that's 0.5 there. Actually, no, that's not real. This is more like halfway. Sorry about that, guys. Oh man. The typos are strong this morning. Okay, so we have our first half-life here, which is roughly here. Okay, so this is t 1/2 for the initial part. And then let's cut this in half again. So we'll come down here and go 0.25. Okay, so that's the first half-life here. Now, if you go out to the second half-life, you'll see that it is much longer than the first. Okay, so t 1/2, the second one is much longer than t 1/2 of the first one. In a second order reaction, the half-life is dependent on the initial concentration. So it's not going to be the same. And as a matter of fact, it gets longer as the concentration, or as the reaction goes further. Okay, so that's first and second. Let's come back to zeroth order. Okay, I know that we did these kind of out of order. Let's come back and do zeroth order and look at the half-life. The integrated rate law for zeroth order reaction is AT is equal to negative KT plus A naught. Okay. So if we plug in a half-life at T 1/2, that means that here we need to plug in 1/2 A naught. Okay. So basically doing the exact same trick that we did before. So we have 1/2 A naught is equal to negative K T 1/2 plus A naught. Okay. And if we solve for the half-life, I'm just going to write it out here rather than going through all the math. You guys can do that on your own if you want. We find that T, the half-life for the zeroth order process, ends up equaling A naught divided by 2 times K. Okay? And again, just like second order, but unlike first order, the half-life depends on the initial concentration. Okay? But instead of being on the bottom this time, it's actually it's in the numerator, which means that, so first of all, let's write it out. It depends on the initial concentration. But since it's in the numerator instead of the denominator, what actually happens is, as the reaction progresses, the half-life gets shorter. Okay, so the half-life decreases as the reaction goes forward, which is different than the second order, where the half-life increases as the reaction progresses. Okay, so in the case of zeroth order, the half-life gets shorter and shorter. Again, let's do a straight line here-ish. Let's draw this out on a graph. How does this look? So if we have concentration here at time t, and we have t on this axis, and we start out at 1.0 molar, first order, or a zeroth order reaction is a straight line. Okay, so we can mark out the halfway point, 0.5. Okay, that's the first half-life. Okay, that's the first half-life. Next, we can come down and do the second half-life. And since this is dependent on the concentration, we'll see that the half-life actually gets shorter. Okay, so this is the second half-life, and you can see that it's quite a bit shorter than the first. And if we come down to 0.125, again, it gets even shorter. Okay, so as the reaction progresses for the zeroth order reaction, the half-life gets smaller and smaller. Okay, so that's half-life. Simply means the amount of time it takes for half of the reactant to disappear. And as we've seen, sometimes it's dependent on the initial concentration in the case of second and zeroth order, but other times it's not in the case of first order. Okay? Now, one thing we haven't really discussed yet is how the reaction time or the reaction rate depends on temperature. Okay, so how does temperature, big T, affect reaction rate? If we think about this for a little bit, we realize that temperature should indeed affect the reaction rate simply because at higher temperatures, you should have more thermal energy available, and therefore you should be able to react much faster, given the delta H of the reaction. Okay? So at high temperatures, generally speaking, reactions speed up, and at low temperatures, reactions slow down. Okay. So if we write out our reaction rate law, rate is equal to K times A to the nth power. This is our general simple rate law. The temperature dependence is not so obvious from this reaction, or excuse me, from this equation. Okay, it's not so obvious, but it turns out that the temperature dependence is contained in the rate constant. Okay, so it's contained in K. K is dependent on the temperature, and K is only constant. Constant at constant temperature. Okay. So if you change the temperature, the rate constant will change, and therefore the rate of your reaction will change. And actually, if the temperature goes up, then the rate constant goes up. Okay. Let's check the time here, see how we're doing. Okay, we got some time. So now we get to talk about one of my favorite chemists. Okay. In 1889, a Swedish dude by the name of Svent. Isn't that an amazing name? Svent Arrhenius. Svent Arrhenius came up with an equation that relates the rate constant to the temperature. Okay, and this is called the Arrhenius equation. And what he came up with was K is equal to some factor A times an exponential raised to the EA over RT. Okay. So let's break into this. By the way, here's the temperature. So K is dependent on temperature. Let's break into this and talk about what each one of these symbols means. K is of course the rate constant for the reaction. Whoa, that's really bad. A is something called a frequency factor. Okay. EA is the activation energy. R is the gas constant that you guys know and love. And temperature is, or T is temperature in Kelvin. Okay? So let's get into each one of these and talk about what they mean individually. Actually, check and make sure I have enough time. Yeah, sure. Okay, so activation energy. Let's talk about this one first. Activation energy. This is sometimes called the activation barrier. And the activation energy or the activation barrier is simply the amount of energy that you have to put into a system in order for it to change from a reactant to a product. Okay, so let's look at this on an energy graph. So this is energy here. And if I start out with the energy of the reactants, and I have the energy of the products down here. Okay, there is a sloped line between the reactants and the products, and it goes down. So the energy is going down here. So this is a favorable reaction. However, to get from the reactants to the products, you have to overcome what's called an energy barrier. Okay, and this, by the way, this x-axis is the reaction progress. Oops. Okay, so as the reaction progresses, you have to go up in energy, up in energy, up in energy, and then you can go down in energy to the products. And the final products will be lower energy than the initial reactants. This energy that you have to go up is called the activation energy. Okay, So even though the amount of change between the two, so delta E is negative, so it's favorable. It's a favorable reaction, but you still have to put in some energy. So you still have to put in some energy to get it to happen. Okay? And this is called the activation energy. Okay? So that's the EA. Next is, we need to talk about A, this frequency factor. Okay. The frequency factor is essentially the number of times or the frequency of events. Well, maybe we should say, instead of events, attempts. The frequency of attempts that the reactants try to surmount the activation energy barrier. So it's a number of times that the reactants try to get over EA. Oh. Okay, so number of times, well, basically it's a frequency, so it's a number of times per second that the reactant is trying to go from this point up to here. Okay, so it's doing this thousands of times per second, and this is the frequency factor. Okay, so however many times it actually does that per second is the frequency factor. Okay. So that's EA. So I'm going to stop here and put this up on YouTube, and then we'll come back for part 2. Okay, so take a break, stretch your legs, think about something else that's maybe more interesting, and I'll see you in the next one.